Good afternoon, everyone. My name is Janelle Edens. I work in the Office of Advanced Fuel Technologies, and I'm the Program Manager for the Advanced Reactor Fuels area. I also have here with me Dr. Frank Goldner, who is the Program Manager for the Accident Tolerant Fuel Program. We also have the technical point of contacts, Stu Malloy, Steve Hayes, and Yutai Kato on the line. So today, Frank and I are going to give a brief overview of the FY18 NEOP work scopes for the advanced fuels area. I will present the first two areas which are relevant to the advanced reactor fuels area, and Frank will present the third area which is relevant to ATF. We wanted to start off by giving you an overview of the Advanced Fuels Campaign. There are two main programs that we support. We have the Accident Tolerant Fuel Program, where we're looking at light water reactor fuel with enhanced performance and safety, which should perform or will perform better under accident conditions than the current technologies. We also have the Advanced Reactor Fuels Program, and this has been primarily focused on developing fast reactor fuels. And in recent years, we've been developing transmutation fuels for waste management missions. And these fuels represent compositions that you would see if you used recycled spent nuclear fuel for the feedstock material. So these fuels include plutonium, americium, neptunium, and rare earth fission products. Okay, so this slide shows the FY17 awards that were made in the advanced fuels area. We had 3 individual work scope areas and we made a total of 8 awards. So now we're moving into the 3 work scope areas. The first is FC-2.1, benchmarking microscale mechanical property measurements. And the technical point of contact is Dr. Stu Malloy from Los Alamos. This slide gives a bit more detail on what exactly we're looking for. There has been a lot of development on microscale measurement techniques in recent years, and we have been able to demonstrate that mechanical properties can be measured on the nanometer and the micrometer length scale. And this is especially useful for the fast reactor cladding program, since we need to investigate how these cladding materials behave at very high doses. And we don't currently have a fast test reactor in the US. And even if we did, it would take several years to get up to the dose rates that are of interest to us. So we have been using ion beam irradiation to get up to those high doses in a very short period of time. But one of the downfalls or setbacks of ion beam irradiation is that the damage depth is very small, usually in the range of 1 to 10 microns. So we really need these microscale measurement techniques to be able to investigate the mechanical properties. But these techniques are also relevant for neutron irradiated material. And one of the benefits there is that the test sample is so small that the dose rate is very small. So that gives us a lot of flexibility in which instrument or facility that we could analyze the specimen that we probably couldn't for a larger test sample. So there have been several techniques developed to date, including microtensile, microcompression, microbending, and nanohardness. However, there's been very little development on ductility measurement techniques. So in this work scope area, we're looking for applicants to benchmark these microscale techniques against the more traditional macroscale techniques, and also to investigate how the data that we get from these microscale techniques applies to the bulk material properties. And finally, because there's been little development on ductility measurement techniques, proposals that include ductility as one of the techniques will be given higher priority. So moving on to the next area, FC 2.2, Advanced Fabrication Methods for Metallic Fast Reactor Fuels. And the technical point of contact in this area is Dr. Steve Hayes from the Idaho National Lab. So I wanted to start off by first giving you an idea of what we're currently focusing on in the program. We're looking at fabrication techniques for these transmutation fuels that minimize the process losses. So we have a goal to get to less than 0.1% of loss of actinide material. Also, because we plan to use recycled spent nuclear fuel, this material has to be handled in a hot cell, so we would need to investigate remote fabrication techniques. We're also fabricating fuels that contain coatings and liners, etc., to mitigate FCCI and to improve the fuel performance. We've also been looking at ways to improve on historical casting methods that were used back in the EBR2 days. And some of the improvements that we've made are we now use reusable molds and crucible materials. We cast under pressure to minimize the loss of americium. And we're also using a downpour gravity casting method versus the counter gravity injection methods that was used for EBR2. And we're also investigating advanced fabrication methods such as extrusion and continuous casting. And these methods allow us to look at more unique geometries such as annular fuels that do not have that sodium bond. So in this area, we're looking for proposals for novel fabrication methods that will improve upon the economics, the manufacturability, or the fuel performance compared to existing techniques. And we're also looking for methods that would get us to that less than 0.1% loss goal. So I would strongly advise that applicants would describe in their proposal how their proposed method is an improvement upon existing techniques and how their method can get us to that 0.1% goal. We're also only interested in metallic fuel fabrication, so oxide fuel fabrication will not be considered. And finally, we understand that it's difficult for universities to work with nuclear materials, so the use of surrogate materials is acceptable, but it's incumbent on the university to select that material and also to justify to us why this material would be representative of fuel compositions that we are interested in. And with that, I'll turn it over to Frank. The mic.
How do you do? I'm Frank Goldner, and as Janelle just said, we work together in the Office of Advanced Fuel Development. I'm going to tell you a little bit about an area that's of great interest. I'm going to jump past the slide of the detailed comments. The technical point of contact is Dr. Utai Kato at Oak Ridge, and I think he's on the line, and I'm sure he'll look forward to hearing any questions of interest. But let me jump ahead and just tell you a little bit about why this is such an important area to us. We've been doing this program now in accident-tolerant fuels for about 4 years since we got congressional guidance in 2012 to within about 10 years to answer some questions and be ready. And we got several main areas of development which can kind of be classified as taking the current fuel and maybe looking at coatings and improved fuel. Or there's one where we're looking at an advanced steel that's being pursued by one of the companies. But the area of silicon carbide, 6-6 composites, has loomed very early as a long-term potential with high payoffs, but lots of questions. And 2 of our 3 companies that are involved in our program, both Areva and Westinghouse, have concepts that involve this. And recently, the utilities have become very interested in our program because they're looking forward to some future time when maybe with some of these accident-tolerant fuel concepts, they can simplify some of the expensive items that are in an existing generation of reactors in the safety area. There's kind of a hope that a combination of the accident-tolerant fuel and some other characteristics of the reactor, like pumps that will keep water flowing, etc., might have a combined effect. And so there's a great interest in 6-6 components, composite cladding, which has been probably, as I recall, at least for 20, 25 years have been under development. Some of the companies that initiated development are still involved with us today. And so they've gotten very interested in it. Of course, there are some very serious questions of uncertainties. And so we're kind of caught with trying to have something done sooner rather than later, and yet needing many years to answer some of these questions. And I think this solicitation attempts to get into some of the biggest areas of difficulty and challenge. And so, I simplify them. to saying, the failure of a silicon carbide, just like glass, is not easy to predict. It doesn't have a nice, simple yield point that you can go looking for. There's a lot of statistics involved. And also with these type of clads we have, being that they'll be in a tubular shape, there are complicated three-dimensional behaviors on these. And so we are looking for work that can look into how these things fail. So one point I would make right away, it's very important that if you want to get into this area, that you look very carefully to understand what's on the table. Because we can't just begin from scratch. People have been working for a long time on this. We've run some experiments, as you'll learn. So it's a major area, the question of fuel failure criteria for these complicated composites. Okay, the second area is radiolytic assistant corrosion behavior of silicon carbide. We've learned that depending on the coolant chemistry of the water reactors, whether they're BWRs or PWRs, it can have an effect on what happens at the surface of these silicon carbide composites. And there's a real question. There's a real question whether we're going to have to do something to protect the surface or not. So again, it'll be very important if you like this area or have something to contribute in this area that you try to understand very carefully why clearly it's different from a BWR than a PWR. Okay, and again, Dr. Cato will be glad to support you, and people at Oak Ridge and others, and also the vendors that are involved. They also will be very interested because they have to answer these difficult questions in the future as they get into licensing and things like that. There is very great pressure. Just for background, our program was aimed at having by 2022 at least lead test assemblies or rods in commercial reactors. That was kind of our congressional mandate in 2012. Well, the utilities don't want to wait till 2012. They want it even sooner. And I just saw some articles, and they're actually talking about maybe putting things in the 2018-19 time period. Well, I just saw an article where somebody wants to do it right away. And, they were really challenging questions. So understanding what the issue is as a function of like hydrogen content, et cetera, pH, the behavior of silicon carbide under different prototypic environments and maybe off-normal environments. The last question is whether barriers are needed for SiC composites. And what kind of technology could be used? There's a problem if you're going to bond a coating on silicon carbide. Let's say it's a metal base or something like that. There's a question. And we've had NEOPs in the past. And so I think it was raised in one of the other slides that Janelle talked about. Look into the past NEOPs. Please research what's been done, because we have had programs and proposals in the past of bonding things. So again, the people at Oak Ridge will be glad to help you. The people at the industries will help you. But it's very important in order to be useful within the limited time that we have. This is really a chance to get engaged more for the universities with. I don't know if you noticed, but on the slide that Janelle showed on the NEOPs last year, I think I had three. I had three NEOPs on just the question of nucleation at the surface of some of these accident-tolerant fuels. Just from the microstructure level, how does boiling really start off in a severe accident? So again, look at the past, and for example, that could apply to things you're considering. The people are doing these tests on understanding the nature of boiling under accident conditions. They will have different surfaces, or they need to know what kind of surfaces are being considered. So I can see some real interaction between what things we've done in the past and what we're doing now. So that's why on this slide on the bottom, we say we're gonna really give a lot of priority under the program relevance criteria that's used up front at the LOI and at the thing, that you show an understanding of where we are, what needs to be done, and how you can contribute in a couple of year time. Of course, with luck, this will develop into other activities that the program could support and would be interested in supporting. So now I'm getting back to just talking about the general for both of us. Okay, so again, as I said just before, it's very important to show relevance to the existing activities that are going on in both areas because time is short. We both have a lot of work to do in the near term, especially as you've heard in the NEAT presentations and all. A lot of that modeling has relevance to what we're doing, and we have relevance to what they're doing. So I see a real interaction across the board on things that you've heard today at other efforts. Okay, and so it's very important to review all the previous NEAPs, not just the last 3 years. I mean, go back, because like this silicon carbide area started about 20 years ago, almost with some NEAP type funding. And it's evolved over the years through SBIRs and other things. So very important to review the past, and the people at the laboratories will help you. I can't underplay the importance of the labs that you've heard mentioned: INL, LANL, ORNL, ANL. They know the past. It's very important to look at the timeliness. The period that these cover is very short, 3 years or whatever, and so again, try to be reasonable in what you can do in those 3 years. Sometimes I get NEAPs that they're going to solve the world's problems in 3 years, and I just got very frustrated looking at a final report from a program, and the guy had promised too much, and so when we read the proposal, it was really exciting. He was going to answer our dream, and what I see now after 3 or 4 years, there's just data, and I don't even get a recommendation. So that's something I'd also like to mention. As you head toward the end of your project, we really would like to know whether you succeeded, of course, but if you didn't succeed, should we continue? Should we try another call? What are the next steps? I think it's very important, and I say this to everybody who's listening in. I've been a little frustrated by after 3 years, I got a pile of data, so very important is at the end is tell us whether we made the goal that you promised in the wonderful LOI, or we need to do more work, or we should have another call, okay? Proposals. Again, you've heard a lot in the modeling area earlier today, and obviously we think you should try, if possible, at all possible, to link up with something that's on that beautiful table of things that was just shown in the previous presentation by Dan. Look at all those models there. Those are models that we're all interested in involved. So try very hard to tie up to filling in a gap perhaps in one of those models or something like that. So I'm impressed how everything fits together. That's why that's that last program with NEAMS. So this is very specific application, but it clearly fits into what everybody's doing. We're all working together to try to make this thing work. Here's your contact information. In my area, it's Dr. Cato, and as you've heard about Dr. Hayes and Dr. Malloy in the other areas, they all know a good part of all the program. So you have general questions, I'm sure they can all help you. I just want to jump to the last slide. We had a good break. Last week, Oak Ridge just published this handbook, Material Properties of Silk Cladding. I was very pleased that just came out, like I think 2 days ago or 3 days ago, I was notified it. The people, the authors of this, and you see Dr. Cato is one of the people, they would very much like your feedback, whether this has been useful. Is there data that it should have that it doesn't have? So I think this is a real opportunity because there's always a difficulty of what basis you should attune. What kind of silicon carbide are we interested in? Alpha, beta, or something like that. So this should help a lot. So I'm really pleased that this just came out in the nick of time. And clearly you see the other references given for Janelle's area. We've got a lot of good documents in the system if you know they exist. And there's one on the nuclear fuel site at INL, Advanced Fuels website. That's a pretty good site because depending on which box you click on, you can find a lot of background information of why we're doing the area. So I'm glad to see that. So I think now I'll just stop leaving time for questions and all.
Okay, we will take questions. You can use the question box on your GoToWebinar. I am going to unmute Steve Hayes
And
Utai Cato and Stu Malloy. I'm just looking for him here on the list so they can answer any technical questions that need to be a little bit more in depth. Okay, I've unmuted all three of you. Can you confirm that that your mic is on? Steve, are you there?
Steve.
Utai, are you there?
Yes, I am.
Okay, great. We can hear you. And Stu, are you there?
Yep, I am.
Okay, great. We have quite a few questions, so we have about 8 minutes, so we will go through as many as we can, and then we will answer any of the others on the nup.gov website. Starting FC 2.1, should proposals include ion beam irradiations or testing on ion beam irradiated materials?
I think it would be very relevant if you could look at the ion beam irradiated material, but that's really up to you how you plan to demonstrate that microscale technique. Alex, do you add anything else?
I agree with what you said there. I'm getting a lot of background, but yeah, that's fine.
Here, let me see if we can cut some of that background noise out. Okay. Utai, it appears that it's your mic that's giving the feedback, so I have muted you until we get some FC 2.3 questions. So another question for FC 2.1, are there materials that are of special interest?
So in this particular call, we're more interested in actually looking at the techniques. If you want to use an alloy that's of interest to the program, such as HT9 or an ODS alloy, that's great, but we're really focused on the technique itself. And we would prefer if the correlations would be applicable to a range of materials, not just material specific.
For FC1 or 2.1, is the tested material just limited to fuel cladding? Would other structural materials like stainless steels be included?
Right, so we're focused on the measurement technique, so it's not specific just to cladding material. Any material would be relevant as long as you can demonstrate and benchmark that microscale measurement technique.
Is there interest in mini specimen techniques for fatigue?
I'm going to let Stu answer that one.
Yeah, that is a area that's difficult to measure at the micro scale. So yes, there's interest in that in fatigue measurements. Yes.
Also for FC 2.1, could you expound on what is needed for ductility measurement techniques? Tensile tests traditionally give ductility information. Is this solicitation going for something above and beyond what a traditional tensile stress strain curve can give?
And I'll turn that to Stu.
So I guess to answer that first part of the question, the main ductility measurement that we would like to be able to measure is what you would typically measure in a tensile test. So that would be one area, but also other very difficult areas to measure ductility in are measurements such as fracture toughness or ductility that you would measure through, say, a Sharpie test or something like that. Those would be applicable also.
Okay, moving on to some FC 2.3 questions. Yutai, I am going to unmute you for these. Will we be penalized if we address all three areas of the scope if we have prior experience with 6.6 LWRs?
I think I can answer that. The call says one or more, so you can address more than one, in my opinion.
I agree.
What are the environments that 6.6 composites are of specific interest to the program?
Well, that's exactly why you'll want to check. But basically, it's the environments of the PWR and the BWR that might be using this material. Our program is supposed to enhance the accident tolerance of existing reactors. So basically, it's the environment of the existing reactors that's of interest.
Frank, where can you get a copy of the handbook, the ORNL handbook that you mentioned in your presentation?
Well, if you can't yet get it off OSTI, Dr. Kato, can you? I think you could at least ask them. There could easily be an electronic version set. Just send a request to myself or Dr. Kato.
How much simulation work is encouraged to be included in this call?
Well, I think that that has to go along with the question you're trying to answer. I don't know, Dr. Kato, you want to make a comment on that, please?
Yeah, I think that the proposal can be either experimental centric or modeling centric. I don't think the modeling alone is a good idea, but it really depends on your approach. So the modeling assisted experiment will be fine. The experimental validation assisted modeling will be good too.
Can you explain the issue with 6.6 composite related to radiolysis?
Well, we have found I'll turn it over in a second, but I think we found in some tests, depending on the oxygen level in the coolant, one can affect the surface of the 6.6 situation, and therefore, again, it's important to look into what you expect.
Yeah, that's correct. So what we know is that the oxidative activity of the water coolant and the radiolysis combined that enhances that's pretty significantly enhances the corrosion rate. Plus the radiation damage in silicon carbide also enhances the corrosion to an unknown extent. But the radiolysis assisted corrosion with sort of the systematic understanding of what kind of radiolytical environment and how much of oxidative activities in the water resulting in what the oxidation corrosion of the silicon carbide is an open question, and that's a very extremely important question for silicon carbide.
So we only have time for one more question. There are about a dozen extra questions, so we will pass those on to Janelle and Frank and their technical team to be able to answer those, and we will provide those in writing to the individuals that ask the questions and also on the NUP website. So the last question is, which utility specifically is willing to put new materials in their reactor for testing?
Well, that's really in the hands of the vendors right now. There have been several utilities that are involved. We're talking of people tied up with Exelon. We're talking about other utilities, but there is some quite a significant interest in making reactors available for our concept sooner rather than later.
Okay, thank you, Frank and Janelle. Thank you, all of the technical points of contact on the phone.